My name is Tariq Sharif, and with me is Ian Finder. He is my office mate. We sit in open space, and he's right next to me. So we work very close on the similar subjects here. So we are here and excited to be talking to you guys about what the Azure GPU and other infrastructure support it has to support any of your or your customer accelerated compute scenarios. Before we jump into the deck, can I have a quick show of hands? How many are familiar with what Azure has to offer in terms of infrastructure and GPUs for AI, HPC, rendering, or remote visualization workload scenarios? Can I have a quick hand? We got a couple. OK, good.
All right,
so
great.
We'll have a good, interesting talk. So we are from the Azure team, and looking at all what Azure has to offer. Azure offers virtual machines for really small web apps, for example, that some customer want to deploy, or your workload is requiring machines that are high on memory, or running databases or storing data as blobs into storage-backed machines. Just like these workloads, we have special virtual machines for AI and machine learning, namely the N-Series machines, which offer both Wiz and HPC machines for double precision GPU computation, or single precision for any machine learning and training. We also have FPGAs that Ian will touch upon a bit that we offer through a third-party service today, actually first-party service from Microsoft called Brainwave. And we also have a private preview out there that customers can come and directly play with the FPGAs. And last but not least, we have Crays in Azure now. You as a customer can work with us, bringing a Cray into Azure, and then that Cray machine can talk to other Azure infrastructure to leverage the storage, network, all of the other resources, the GPUs, for example, as well.
So the real point here is whatever the geometry of your parallel workload is, we have a SKU that probably fits it really well.
Yep. So our journey in GPUs started, it'll be 2-year anniversary in production this December. And when we launched, and ever since then, as we talk to customers and they come with problems or their scenarios they want to go and lighten on GPUs, they don't come for one thing at a time. And more often than enough, it's more than one problem space that they're looking a solution for. And looking at the portfolio of customers and kind of scenarios they're trying to light up, we have divided, or at least I think of there really 4 work verticals. It's for remote visualization. For example, you want to leverage the workstation in the cloud to do a CAD design or render an image for a print media. Or you are trying to make a video or a movie animation and leveraging GPUs for that, and you want to parallelly do a lot of frame computation and then combine those to make a 4K, 8K, 1080p, 720p, whatever sort of format you want that video to be in. Then also the next vertical is the HPC simulation vertical, where, for example, if you are in medical health sciences and you want to do some trials on some new medicine, rather than doing wet trials right away in the lab, taking different chemicals or solution and seeing how they interact with each other, you can do a lot of those simulations in the cloud before you actually move to wet trials and really cut down the time of getting to human trials from months to weeks and maybe even days in some cases as you get close to finalizing what the final drug is going to look like. And then last but not least, AI, ML, this is all very new, and everybody is trying to bring intelligence to their products, whether it's somebody either working in automotive industry, making the car self-drive, somebody manufacturing, taking that to detect defects on any of the components that are being manufactured. And they don't apply to one industry like automotive. It applies to print and media, entertainment, health sciences, aeronautical, you name it. So it's not just one area any particular industry is looking at. They look at all of them in some cases. Building onto this theme, let's take automotive, for example. Automotive, you want to design a new car. Everything starts with first wireframing it. For that, you need workstations in the cloud. You need a VDI solution in the cloud. And the other thing to keep in mind is, based on how diverse the workforce is now, some folks, for example, let's pick Honda, for example, right? They have development centers in Ohio. They have development centers in California. They have development centers in Japan. And if you're trying to make something that is really great, everybody's trying to collaborate on the same thing. They are trying to work on the same model. Somebody might be designing the hood of the car. Somebody might be designing the drivetrain of the car. Somebody might be designing the suspension of the car. And at the end of the day, that data has to come together to look the product as a solid, cohesive thing. And then also, if somebody has the wireframe now, Then the designers will take that same wireframe and run it through some rendering on how will the car look like in sunlight, in fog, or in the evening, how the hood is going to reflect if you are driving on a coast where the sunset is happening. You don't want to be having glare coming to your eyes. And you take the same model then, and you run it through some HPC simulations. We'll talk about that in a second. At the end, and also at the end, you will take the same car, you will put some smart devices on it, and have it collect data and also respond to data if you're trying to detect lane departure or like you're trying to do adaptive cruise on it. So all of, at the end of the day, is working off of the same data set, for example. And Azure or the cloud is the place where you want to do all of it. So that's where we come in, and we work with other solutions in Azure and provide a one full end-to-end solution for it. Also, it's not just the high-end CAD applications that need GPU power in the cloud. Everyday application like my PowerPoint, for example, is leveraging the GPU on the machine. Maybe it's a tiny utilization, but it is leveraging to have a really smooth animation from slide to slide. Or your browser, HTML5, and playing a game online, or any of that. All of those are now leveraging GPUs in the cloud. And to power all of these experiences, we have the Microsoft N-Series, and V stands for visualization SKU or sizes to offer, which is backed by the NVIDIA M60 or Maxwell GPU. They come in 4 different virtual machines that customers can provision, and that is based off of the workload requirements. I mean, you can go provision a machine with 1 GPU. It comes with 6 cores, 56 gigs of RAM, or you can go provision a machine as high as 4 GPUs in it, has 224 gigs of RAM in it, and it really boils down to the workload, how many users are going to be on that machine, whether it's a 1 user to 1 workstation scenario, or are you going to do a VDI deployment where you may have multiple users come to the same machine. Another interesting vertical that's being used is gaming here, where the game companies are using these machines to publish the game, and then they are using these machines to stream the game to multiple devices like phones, iPads, small, tiny laptops, where all the rendering of the game is happening in the cloud, and you're just streaming bit by bit, frame by frame, and having the user play the game. Just this Monday, we also announced the availability of the NVV2 preview. It's based off of the same NVIDIA M60 platform, and there are 3 main additions we are doing to this. First of all, we are adding the support for premium storage to these machines. What that means is if your application is IOPS intensive, any CAD application that is trying to quickly load the models or quickly write down to the disk as the model is being rotated, you need support for fast, high throughput, disk here. So we now have support for premium storage. And actually, it will also support Ultra SSD when it's available worldwide, because it's only in preview right now. Also, we are doubling the amount of system memory on it. And that's where we are going after the workloads like petrol in oil and gas, where there are data collectors, machines that go and collect seismic data on underground or onto the surface, and then you take that data, run through simulation, and then you load all of the data on a screen, so where an engineer can say, this is the place I want to drill. Because drilling is expensive, and if you miss that drilling, you have wasted not just money, but also time and the opportunity cost over there. And then also, we are upgrading the CPU class on these machines from Haswell to a Broadwell-based CPU. And last but not least, very important point. Any of the Quadro functionalities you leverage today on NVIDIA platform, you need the grid licenses. Today, if you have on-prem deployments, you have to deploy FlexLM server, for example, to NVIDIA grid drivers to say, yep, I am licensed for the functionality, and this user should be able to leverage. We actually, in Azure, have worked out with NVIDIA where none of that FlexLM server is required when you're leveraging these machines for visualization workload. And the price that you pay for these machines per hour includes all of the overhead of licensing it. So you, as a customer, or your customers, don't have to worry about any of the licensing setup, licensing requirements, how you're going to polish the users. It's just built into the VM price. It's not only the infrastructure. We also have a great partner ecosystem story, and I'm going to pick 2 as use cases. So one of them, for example, WorkSpot. They are a company based out of California, and they have really optimized getting the CAE customers or AEC customers getting a workstation up and running with Revit on it. They can go to a customer and get them up and running within a matter of days, as opposed to taking months to getting the infrastructure up and running, evaluating the apps, seeing how the user experience is going to be. They have shortcutted all of that, and they can get from 0 to production in less than 60 days. Also, Teradigi is another good partner where the color accuracy is really important for some industry, namely the media entertainment. They want to make sure that the color, the purple color that's being rendered, is actually looking purple when they are interacting with it, when the user is going to see in the final movie set, for example. And we have full support for the Teradigi PC over IP protocol, which is optimized for accuracy and low latency and network that don't have the bandwidth that is not, for some reason, the customer is getting. Also, last but not least, on this slide, we also have a complete story for deployment with the newly announced Microsoft Virtual Desktop service. Just like using Microsoft Virtual Desktop, you can deploy a non-GPU-based machines like on D-Series or F-Series. You can also go and provision N-Series machines with them and have a complete deployment story in your organization, whether the workstation or machine requires a GPU or it doesn't require a GPU. Let's take a quick look at a demo where I'm going to start off the demo, and then Ian will take from me in a second. So this is my NV machine running out of US West, and I'm going to run one of the industry benchmarks, namely Unigen here. And you're going to see that even though this machine is 4 GPU-based machine, but the workload or the application here is only going to leverage 1 GPU. So it's all going to come down to what applications you're going to run and what is the application requirement in this case. As you can see, this is reaching up to 50, 60, it's going to go to 100 frames per second as more textures are loaded. And on my Perfmon, you can see that only 1 GPU is starting to get utilized. And soon I'll show you a case of where an application actually uses all 4 of them.
What you can kind of barely see at the bottom there too is I have a GPU session up in a second remote desktop session. You can kind of see it there. I'm running a not very taxing thing.
Yep.
It's using one of the other GPUs.
And also at the same time,
box.
on the same machine, I am, for example, with my designer hat on, I'm designing the wheel for the car. And I can easily manipulate the weight in various views and with smooth animations, and all happening this in real time while the GPU is at the same time utilized by another application. At this point, I'm going to hand it to Ian, and he's going to run us through some additional interesting scenarios.
So if you can quit that for a moment.
Yep.
One of my favorite use cases for VDI is actually in the medical industry. I don't know, show of hands here, who's had a CT scan or an MRI done? If you feel comfortable answering, of course. I certainly have. The data sets that are produced by those scanners are actually quite large, and there's when a medical professional goes to actually review that 3D imaging, a lot of times they do it on a workstation class machine with a large NVIDIA card that sits very close to the point of care, the scanner itself. In diagnostic imaging, there's certainly a scenario for large hospital systems, many of which are already leveraging thin clients. My personal hospital that I go to, if you notice, there's thin clients everywhere connected to a remote Windows machine over, in their case, Citrix. But they don't have GPU workstations in every room. A doctor can't just walk up next to your bed and review your 3D diagnostic imaging from a CT scan or an MRI. So I really like this demo because it shows, you'll have to pardon the kind of video quality. That's the con Wi-Fi doing me in there. But these are actual scans that normally would take a high-end workstation to manipulate. And one can imagine a nurse or a doctor reviewing these at the point of care, bedside or whatnot, through an iPad, through a tablet. This is a really powerful use case that we've come to hear about from the medical industry. So this is kind of just to show some of the deskless viz scenarios. Tarek ran his demo. I've got this, and then we'll move on to some other industry and media verticals.
And the thing to note here again, this is still accelerated compute. This will not work as smooth rotating the model around if it was just a CPU-based machine. So for this, you need a powerful machine, and GPUs in this case help immensely. Go to the next one. Ian, ready?
Yep. So this is just a little bit on how all this works. Certainly, a lot of people are confused when we tell them we're putting real GPUs, real hardware on virtual machines. The way we do this is we actually have some changes to the host OS and hypervisor. At the bottom of all this is that pool of 4 GPUs that Tarek talked about. In the case of the demos you just saw, those were NVIDIA M60s, but we have V100s, P100s, P40s in the service as well. Those are passed through directly to a virtual guest real GPUs, virtual guest, through a scheme we call direct device assignment. And basically what that means is we have custom code in the hypervisor that works with the Intel I/O MMU to virtualize the real hardware and the real PCI endpoints for that hardware and pass them directly down to a virtual machine with very little overhead because, again, we're leveraging the I/O MMU on the host machine. It's not being emulated. The calls aren't being wrapped. They're full native calls to native hardware from a virtual machine. And with this, you can use any advantage that you already have in the Azure ecosystem. These aren't like bare metal machines where you have different considerations around your infrastructure. Any Azure image, any Azure Marketplace image, any drivers you have, they'll work the same way on these virtual machines as they work on a D-series or an F-series because of the way we virtualize this.
And also Windows 10, Windows Server 2012, Linux, Ubuntu, CentOS, you name it. It's a bare metal machine almost with full access to the GPUs.
All right, so one of the next big workloads for this kind of thing is rendering. And this is when you've already taken the visualization you've done in your design lifecycle. You've modeled something. You have this geometric model you've built, and now you want to put it into print or into media or just show it around to the people in your design group to kind of figure out what it looks like. In many other cases, we also have motion picture customers who actually do large-scale rendering on GPUs. Photorealistic rendering, not to be confused with the real-time visualization. So in this case, I have a CUDA-aware renderer that actually will use all 4 GPUs in that box. It runs CUDA code, and CUDA, for those of you unfamiliar, is NVIDIA's general-purpose programming model for the GPU. So when I press play here, I can open up the performance monitor, and the first thing you'll see here is the CPU usage is going up, and it's actually compiling the scene to something that the GPUs can run. But in a moment, that CPU usage is going to drop off to almost 0. And those 4 GPUs are going to take over ray tracing this photorealistic scene. And in this way, render customers who would normally do this on a CPU would take hours to even days to trace out a photorealistic scene. But by using the parallelism of each individual GPU, and then even the parallelism across multiple GPUs, we can trace out a photorealistic image with realistic reflection, highlights, refraction, depth of field, the kind of stuff our motion picture customers and our design customers love. We can do that in, orders of magnitude less time. So you can see that filling out, and if I leave that for about another minute, it'll start to look quite real as each ray of light comes in. But I'm going to cheat a little bit, and I'm going to show you what the finished product looks like.
And we did that just about an hour ago as we were getting ready for these final set of demos.
Yeah, in fact, these aren't even finished. These are just more rendered. You can really kind of dial it up to a quality level that you feel is appropriate. But this is the kind of thing that historically and even today on a CPU would take many, many hours. And this was done in under 1 hour. So there's a big cloud advantage here, too. We're not just doing this in the cloud because we can. In a typical artist lifecycle, again, you start your modeling process. You take the actual geometric models, you build textures around them, and then you execute third-party plugins to maybe wrap the textures. We have a solution for this as well that I'll talk about. You export your work to assets, and then you render it. And rendering is really where the large-scale compute costs are incurred. By having VDI as well as HPC for the render side of things, where you actually have to do lots of work on these assets you've created, having storage, and having a third-party plugin ecosystem all in the cloud, we can capitalize on the locality of all that data and allow people to work remotely on productions that normally would require large-scale investments in infrastructure in-house. That was actually the demo for rendering, but Tarek has another demo to show you, which is how you take something like the render I showed you and parallelize that to like a full motion picture level or a full car design kind of level where you have a lot more rendering going on.
Thanks, Ian. So you saw you can do this at a frame at a time at a much faster speed than what CPU would have done. But how do you do this at scale? You can't be doing frame by frame, workstation by workstation, person by person. You want to automate all of this. For that, we have a service in Azure called Azure Batch Rendering. Batch is a general purpose scheduler in Azure that can take your input file, which is a job file, where you define what is the application, for example, I'm going to launch, and here are the additional parameters that I want to be passed to the application. Here is my storage location where any output of the app should be saved to, and here is the kind of machines that I want to launch here. With that, we have added the support for applications like Maya from Maya or 3D Max or Arnold or from Chaos Group's the V-Ray app. And we have even built in per minute licensing where we license this from these software houses where you don't have to worry about setting up any special contract with them. And then you as a developer or some of the artists in your company can then submit jobs, meaning you define the asset, you define the layout, and you submit the job. And as the job is processing, you can actually in the middle see what the frame output is looking like. As we saw in the app, rays were being traced, image was getting better and better. You can do the same thing in Azure Batch on any of the supported tools where you rather than waiting for the entire job to be done, you can any point take a snapshot what this thing is going to look like, reset, start it over again, modify it, enhance it without having to have a complete job done.
I want to talk really quickly about what a big deal pay-per-minute licensing is for our media entertainment customers. Normally, let's say you model something on your laptop and you want to render it in like 30 minutes. You need thousands and thousands of cores to do that. And typically, the software is sold by the core. So that's prohibitively expensive to just burst and render something for a half hour on 1,000 cores and then stop. That pay-per-minute licensing is key to getting these customers on board in a model where they can burst render things.
Okay. So for demo, I'm not going to actually go submit a job, but I'm going to show you the walkthrough of the assets that I took and output that I had and how I went about creating those. So first, I defined the job file. In the job file, I said that, hey, I want to provision machines of NCV2 type, which are P100s in this case, and I'll talk about these in a second. And the applications that I'm going to utilize in my job is V-Ray and 3D Max. Then also in the job file, I define what is the characteristics or the two of the attributes of the image. It's an 800 by 600 pixel image I'm going to want, and I'm going to launch 3D Studio Max, and here are, for example, the additional parameters I'm going to pass to the application. When I run the job, first thing I'm going to define is I want total 30 machines. But I've divided my 30 machines into two pools. One is 10 regular priority VMs that I paid whatever the listed price is, and the other are 20 low priority VMs. And low priority VMs are great here because you get a regular VM if capacity is available at up to 80% discount. So if you are, for example, doing all of the work today, creating the assets, and you're leaving for the home. And yes, people do work around the clock on some of these things. So there's some capacity available in the evenings, and people go utilize the capacity for that. They submit the job, 80% discounts. And if for some reason there's a high priority job comes in, yes, your job will get preempted with it. But there is some predictability built in the system where we just don't go and deprovision these machines. And then I'm going to say, hey, for my actual job file, I want to have 30 images created, and the images should be named 1 through 30. So this is the Azure portal showing those 30 nodes running, and going into the details of showing 30 nodes that are actually some of the nodes that are actually doing some work, and some that is sitting just active, which is about to go get shut down because the machine is done doing the job that it was supposed to be doing. So let's take a look at what that images set was. So if I go to my assets folder, for example, I had an asset defining what the wall may look like. And then I had another asset that defines what a palm tree I want to have rendered in my image at the end. And at the end of my job, these were the images that were produced. So as you can see, the wall is in the back, laid out. Now think of how many computations might have happened to really trace the light here, reflections here. And here is the wall with the picture and with the palm tree on it. So I got these 30 frames created. I didn't, just for the sake of saving time, I didn't compile this into the video, but if I press the next button, you can think of a video that I can go produce where a scene is being created where somebody's walking into a building, for example. So these are all the images that I produced by massively parallelizing these tasks on multiple machines and getting the answers or the results computed as quickly as possible. Okay, going back. One of the use cases or a success story is Jellyfish. It's a production house based out of UK, and they are utilizing our GPUs for two scenarios. One is these massively parallel rendering jobs that they're leveraging the GPUs for, and actually, if we have time at the end, I will show you a video of there. It's pretty cool. And also, they're leveraging the NV machines for their artists, and they're partnering with Teradici. They actually are shipping a really thin, dumb device to their artists throughout the world to get them up and running, doing design on dual 4K monitors by leveraging the NV-series. So all the data is in the cloud, all the workstations in the cloud, workforce is diversified, so they can have work done around the clock. Folks on east side can work while the west is sleeping, and west can review the results when the east is sleeping, and they can really work on the data 24/7, literally. Moving on. We have done visualizing the car. We are done designing the cars. Next I want to run some simulations on the car. The car looks very pretty, but does the car do well when it's going through on a road on a very windy day, and it's an electric car? You want to preserve use as little energy as possible on the car. So as you can see in this car model, when I ran through some HPC simulation, which again ran over multiples of GPUs, I can see the drag on the front of the car is very high.
Let the record indicate he drives something with really crap fuel economy.
Yes, I do. Yes. Thank you, Ian. Let's not talk about your car. Okay, so at this point, I'll pick up the phone call. I'll call the design department, say, guys, I don't care how pretty it looks, fuel economy is going to kill, it's not going to sell. So I can go and back, work on the same model, same data, and really turn around data quickly and results quickly by running it through multiple simulations. Or in the case when I was driving the suspension, I can run the suspension through a simulation of going over potholes and seeing how the spring or the shock is going to do. Do we need to adjust these, tension on the spring, have this shock that has a higher damper or lower damper and things like that, really cutting down on the amount of time it takes from design to actual product. To power that, for these computation tasks where you do need double precision because you are doing math to the accuracy here, we have the NVIDIA P100 GPUs offered in a series called NCV2. Again, they come in 1, 2, or 4 GPU machines with 112, 224, and 448 gigs of system memory. And the beauty of this hardware platform is if you ever, and you will actually, whenever you're doing something at scale, will want to go beyond a single node to hundreds of GPUs. And the way you scale and interconnect multiple nodes is a networking technology called InfiniBand, which offers a node-to-node connection at a really low latency and high throughput.
We're actually going to talk a little bit about that, and I'll show some InfiniBand stuff later.
Also, we just this year in March announced the public availability of the NVIDIA P100 PCIe devices, or V100 PCIe devices. So offered in the same configuration, have a lot more throughput in terms of the flops it can do at single and double precision. And again, being able to scale out from a single node to hundreds of GPUs, making it a cluster for these large-scale simulations using InfiniBand as a technology. City of Hope, quickly going to touch upon since we're running short on time, is a drug research company in LA. And they actually really, when they were moving to the cloud, they wanted to cut down on the time to get to wet drug tests from CPU simulations to GPU simulations. And they actually cut down the time from weeks to actually days, doing multiple iterations and seeing which compounds, which molecules, which enzymes are going to interact with bacteria better and have the least amount of reaction to human body, for example, if they're giving a shot to a person. So you want to see the drug and maybe also visualize how the shot and the area around may look like.
And these order of magnitude speedups, even TCO constrained, are pretty typical for the kind of applications that parallelize well to a GPU. We showed a lot of rendering because that's an easy one, but there's computational fluid dynamics, comp chem, stress modeling, the wind tunnel example Tarek talked about, which is CFD. But now we're going to talk a little bit about deep learning and AI, which we talked about viz, render, simulation. The last real bucket that's got a lot of interest these days is deep learning and AI. And there's a reason for this. It's generally prohibitive to train a good DNN model on a CPU. It just doesn't work.
And also tying back to the car story, right? I mean, now you want to make the car smart. All of these automotives are doing lane departure detection,
that's a great
driving, self-driving cars. So
the way you recognize something like a sign in a self-driving car or pedestrian is actually a training data set. You feed the machine pictures of signs, and you say, this is a stop sign. This is a red light. This is a person. Or better yet, you even feed physics simulations into a DNN model where you have the car driving down the street, and you have forces acting on it, and you say, well, this resulted in a crash. Really, how you build these models is the intersection of having powerful computers that can actually build the model for you and having enormous data sets. And that's what's key to making a high-quality model, having a huge amount of data sets that are associated with the outcomes you want or don't want to train the model to understand. Your model will only be as good, if you want a powerful model, as the data set you feed it. And these days, with things like simulations of autonomous vehicles, sensors everywhere, those data sets are getting larger and larger and larger, and that's something we can really, really help with. Kind of like I mentioned, the way we are actually doing autonomous driving these days is people are putting cars in physics simulators and driving them for billions of miles to understand what the forces acting on them are and what conditions contribute to a crash. So they've got their physics model, they're building a data set of what the car's doing and what the outcomes are, and they're training neural networks on that. In many cases, there's an SLA associated with this. We've talked to some retail customers, for instance, who collect all the data, the energy consumption data from their retail stores at the end of the day. There's a multinational retailer, and they model it. So they have to close that model kind of similarly to the way our fintech customers need to run an end-of-day closing. These customers have to run a model and train a model every night. And that takes an immense amount of compute power, which I'll show you in a moment. But to do these use cases, we have a couple different SKU classes. We have our N-Series, NDV1, which are Tesla P40 GPUs. These are optimized for both training models and running models, that is, evaluating the outcome of a deep learning model. They have 24 gigs of memory. We've had them out for some time. They have InfiniBand, which Tarek talked about, which is a MPI technology, a parallelization and clustering technology, which I'll show in a moment. And we also are excited to announce our NDV2 series. And this is the biggest, baddest AI box you can get in the cloud right now. This is 8 NVIDIA V100s with a technology called NVLink. And what NVLink is it's a parallelization technology that lets the GPUs talk to each other in a way that you don't have to leave the box to do. This is important because it means, I'm just going to skip over this in the interest of time, that your frameworks don't have to be aware of parallelism in the same way they would if you were using something like InfiniBand. If you're training a model on one box, most of these frameworks like PyTorch, TensorFlow, MXNet, they can actually do that just right out of the box. They don't need any help. If you have 8 GPUs in a box, you're not actually clustering. So that new SKU is an incredible value prop for that reason. All of these SKUs that we have work with industry standard frameworks that your customers are probably already on. Things like TensorFlow, things like PyTorch. And we're also excited to announce the availability of NVIDIA's NGC containers, which contain a whole bunch of tools that are useful for deep learning applications right out of the box. So if your customers are interested in deep learning applications, they can either use whatever they want from the TensorFlow GitHub, the PyTorch GitHub, or they can use the NVIDIA NGC containers to try out some things out of the box. It's really whatever their infrastructure is on. And we have some tools that help you parallelize your workflow once you have something that warrants it. So if your customer has an algorithm they want to train overnight and they want to parallelize it, we actually have technology to do that. So I'm going to wrap this up here with one final demo. And we're going to take 8 GPUs across 2 machines that are clustered using InfiniBand, and 32 GPUs across 8 machines that are clustered with InfiniBand. We're going to use Horovod, which is a framework built by Uber for distributing TensorFlow work across multiple machines. And it's aware of that InfiniBand network interface that we have. We're going to use TensorFlow, which I'm sure, who here's heard of TensorFlow? It's pretty much the gold standard these days for training neural networks. And we're going to use off-the-shelf components to do this. We're just going to take all the stuff off of GitHub. TensorFlow GitHub, Horovod GitHub. We're not using any special Microsoft magic here.
Except for the machines.
Except for the machines. And a technology that we call Batch AI, which is now under the Azure ML umbrella. And this is a little developer framework that helps you kind of automate the provision and build out of the cluster and the job management around it. It's really cool because it means when those 32 GPUs are done with your job, you can programmatically spin them down so you're not paying for it. So training on 32 GPUs in 1/32 of the time will cost you the same as training on one GPU for 32 times longer, because we have all these APIs around spinning up clusters and bringing them down. So 8 GPUs versus 32 GPUs.
Woo-hoo.
Can anyone here guess how well this will parallelize? Well, first, which do we think is going to be faster? So I'm going to set up a file share to persist all the data, because the cluster is going to go up and go down, but we want to have that model. We want to have the training data. We want to have that all persisted in Azure Storage. And we're going to spin up a compute cluster. And here you can see that I'm using the NC24 RSV3 SKU, which Tarek talked about a little bit.
R stands for RDMA for InfiniBand.
Yep. We're going to make sure our cluster came up, which is probably a good thing to do when you're running a demo. I'm going to start the 32 one as well. Just walk through here. And this is a tool, for those of you unfamiliar, called Jupyter, which is just Python code running in a notebook-style interface. So I can kind of show you one thing after another. But it just uses our standard Python APIs. All right, now I'm going to submit the job.
And what kind of image are you training, Ian, in this?
I'm training an Inception v3 model, which is the kind of model you'd use if you were doing that scenario we talked about earlier, where you're trying to teach the computer to recognize a person or an antelope or a deer or a road sign. It's a pretty standard image recognition model. And one thing a lot of our customers are doing with it are things like defect analysis or object recognition. There was a fun demo we showed a while ago where some guy had a picture of a dog and it would tell you what kind of dog it was. So really just you're at the mercy of your image base and your data set that you've associated with it. But whatever goes in, you'll get a pretty reasonable image recognition model out of it. Sorry, that took a second because we're on Wi-Fi here. But you can see that I've kicked off the big training job across the 8 nodes. And all that InfiniBand cluster interconnect stuff is taken care of for me by Horovod and by this script I'm running on Batch AI. And I'm going to kick this one off as well. I do apologize for the delay here. The network, I'm sure some of you have noticed, is not great. And I can actually take a look at my cluster here. Here you can see the small one, and here you can see the big one. And this is, again, Batch AI, which is part of the Azure Machine Learning family. But this is something we built to allow you to automate jobs, even if they're based on just normal open source frameworks like TensorFlow. And you can see I have 8 nodes here actually running my job. I can go look at my jobs. Oops. Switch back, and it's running. So on the 8 GPUs, sorry, on the 32 GPUs, we are still warming up. In a second, these results are going to start streaming in. There we go. So each GPU is doing 200 images a second. And in a moment, it's going to give me the aggregate across all the GPUs. That's, if you had 200 images in your training set, one GPU would go through it in a second, right? 200 road signs, 200 pictures of road obstacles. So in total, the cluster is doing 6,207 images a second. If I go look at the small one, I'm still being tar-pitted by the network here, but I can tell you that it parallelizes within about 4% of linear from the 8 GPUs to the 32 GPUs, which is an incredible value prop for most of your customers who may be training against an SLA. If they have to have a training job done in one evening, for instance, they're paying the same to do it quickly by leveraging our burstable infrastructure, the ability to bring up a bunch of these VMs and then take them back down and stop paying for them. They're paying the same for that as it would to cost them to get their results in a longer period of time.
Show anything else? Show us back.
Yeah, let's switch back. So finally, when you have your model, you actually have to run inferences against it. That's to take that picture from your sensor on the road and say, is this a stop sign? Is this a stoplight? What am I supposed to do with this? And that's called inferencing. And we have some tools to bring the TCO of that down too. I'm going to touch really briefly. Has anyone here heard of Project Brainwave? Oh, come on. We got to market that better. So Brainwave is a way to actually take your machine learning model that you've trained presumably on GPUs and evaluate it in a service. So when your customers have that app that's supposed to tell them what something is, they can send their request off to a service that can actually evaluate your DNN model cheaply. So Brainwave is going to be announcing new model support, ResNet 152. They already do ResNet 50. 152 is one of the more popular image recognition algorithms. They're also adding DenseNet, SDD, and VGG. With these changes, this makes Brainwave a lot more attractive to our customer base. Before, you'd have a neural network model that you couldn't really run on Brainwave because they only supported one of the very standard image recognition models. They're adding a lot more to their portfolio. And for doing one inference at a time, Brainwave has the industry-leading cost of ownership. There's nothing cheaper for doing DNNs on one image. I'd highly encourage you to take a look at the AML real-time AI stuff. We don't have enough time to get into it now. So to wrap things up, when your customers have high-end compute tasks and high-end deep learning tasks, infrastructure often gets in their way. No one wants to buy an on-premise GPU cluster. They cost hundreds of thousands of dollars, and chances are you're only going to be using it for 30 minutes every night if you have a good degree of parallelism on your workflow. We have tools that allow you to manage and burst your clusters so that you're only paying for them when you need them. We have scheduling tasks so you can make the most of those clusters when you have them up. We provide high-speed access to data so that you can do your modeling, your rendering, your simulation in the cloud, all from one data set that you keep up in Azure. And we offer cost and workflow management tools so that when you have to figure out how much it actually costs to train that big DNN model, you understand what it costs to do that. You understand what it's going to cost, and you understand what it actually did cost on the other end when your training was successful. These are a lot of ingredients that together make Azure a really interesting value prop for these high-end use cases against on-prem.
Cool. Thank you, Ian. So please fill the eval. Wait. I have some things at the end that I wanted to say. I'm going to switch to my other slide deck and show you guys some work that we have collected that really highlights some of the outcomes of what these things can do. We had the training demo done, images per second, but what's the outcome? So here, if I go full screen on it first. Okay, it's not going full screen for some reason. Where's my cursor? Here, Microsoft autonomous driving team actually have built a model to self-drive a car using the NVIDIA GPUs, and they did two things. First, they actually rendered the streets on it. They built a reinforcement model where they told the car just to go drive, and they were giving a score to the car of a +1 or -1. +1 if it did anything right, it made the right turn when it could do it, and -1, for example, if it hit a sign. And the model trained itself to drive on that simulated environment. So here's the Jupyter Notebook. I can provide you a link for it, and you can go to access it. And my cursor is not working. So here.
By the way, our other benchmark just finished. It was 1,500 images a second. So 8 GPUs at 1,500.
So here are 4 simulations running in parallel where you can see the car is driving around, hitting a road, hitting the fence, jumping back onto the road.
Drives pretty much like Tarek does.
No, better than that. And then, so let's go watch it again, what this thing did. So if
I want you guys to really observe how he drives.
Yeah, so it's hitting road, it's getting a negative and positive points. At the end of the day, the model was trained, and if I fast forward this video, and look, the car is driving beautifully. Only like I can't be trained for this.
Is that my car?
Yours doesn't even drive you, and it's in the shop somewhere. All right, so that's one thing that was trained and is available for anybody here working with the automotive industry. Here's the link, the AKMS link, that if you guys want to quickly take a screenshot off and go read more about it. Oops. And then here is the jellyfish demo. And this is what I'm going to wrap up the presentation with. And this is some of the artwork that was built by a jellyfish. And that you may have seen some of this in any of the movies. That was all done on Azure NC and NV series. For NV for creating the assets, having the designers make some rough sketches, and then using the GPUs in the cloud to render these scenes to the full 4K, 8K fidelity and making videos out of it. If you can go full screen. Yes, it's working now. And any questions, please come forward, and thank you so much for coming to our session. Thank you.